All right, cool. Um, so, couple of things up front. First of all, somebody just told me last period that there's apparently a physics exam on Monday, and so I've pushed back the due date on PA5 by 24 hours. So PA5 is now due Tuesday morning at 8 a.m. Um, and it's early enough that hopefully nobody is upset by that. Um, So that's due Tuesday morning. So I changed that in Canvas, and Canvas should have an announcement about that. So it's still due at 8 a.m., but it's Tuesday. All right. The other thing somebody pointed out last period was that the quiz, which is one of the quizzes, I think quiz 5, which is due on Friday, I believe, talks about tries, and we haven't gone over tries yet. So I'm going to talk about tries today, which is another kind of data structure, but we're going to do some more dynamic programming first, but we'll get to tries after that. And then I think you should have everything you need to do all of the quizzes. And the quizzes are good practice for the exam. I also posted some questions a few days ago on Canvas, some practice questions related to sorts and heaps in particular that that might be useful to study and work on for the exam. And as usual, your best way to prepare for the exam is going back through the programming assignments. Make sure you understand everything we've been talking about, but in particular how it relates to what you were coding up. And if you didn't get everything working on PA4, for example, keep working on it. Take what we've talked about since then and try to use that. Come to office hours, get better with GDB, all of that stuff, right? So lots of avenues for preparation. So any questions? Anybody make progress on their max val function for PA5 yet? Starting to, cool. All right. I will give you more details about your SLP probably tomorrow. So your presentations are Monday, as discussed before, but I'll give you more specific details tomorrow, including the Zoom info that you need to come to the meeting area. Once you get there, I will put you into whatever room you've been assigned to, and you'll do your presentations in there. So again, that's during class time, so it'll be 10 o'clock to 10:50. Sorry, 11 o'clock to 11:50 for this section. All right, so hopefully, what we went through yesterday made sense and helps you with the max val function. Definitely try to get some progress on that sooner rather than later. It takes a few tries sometimes, and you can code up the max val function and test it without worrying about the dynamic programming part. You can really add that in at the end. But you can solve small knapsack problems with just a plain old max val function. that just goes ahead and does all the recursion that it needs to. But if you try this with, a large capacity bag with several items in your inventory, it will probably not finish unless you're using dynamic programming. But you can get the guts of it working anyway, right? And dynamic programming is really, here's my function blah. It's recursive. It takes years to finish, right? And so this is my function n. So really, you just need to do two things, right? At the end, save whatever your final calculation was, which might be a number or a set of data or something, but save it somewhere in memory, indexed off of that value n. And in the beginning, check to see if save n is available. Then just use that. And that's really all the dynamic programming piece is. It's just something in the beginning and something at the end. So this caches your result, and this looks to see if your result has been cached so that it doesn't need to calculate it again. The details of doing that depend on the specifics of the problem. So in the case of Fibonacci numbers, we knew that our Fibonacci numbers were never going to be 0. So I could initialize my cache to zeros, and I could tell if something was stored in my cache by seeing if I had a non-zero value. That may not always work for you. You may actually need this to be some sort of structure, and part of that structure could be a flag which says, is this a valid entry in my cache? So save could be a structure that has a flag saying, have I stored something in here? And has a number, which is the maximum value I can get from a bag of that capacity, and has an array of how many of each item I need in order to get that maximum value. So you could define a structure with all those pieces and then make an array of those structures, initialize all your flags to whatever value says there's nothing in this entry, and then when you save, you save the max value, you save the inventory of items, and you set that flag to whatever the value is, saying this is a valid entry. So you got to do some work here, right, beyond just this. But this is the essence of what's happening with dynamic programming. But you want to figure out how you're going to implement that and then make it happen. Will all SLP presentations be finished on Monday? Yeah. So the presentations are just a 50-minute thing. So from 11 o'clock to 11:50. I think 11:45 actually on that Monday, and it will be a Zoom meeting with a number of rooms set up, and I'll place people into rooms. There's a schedule of who's in what rooms, and you'll do your presentations in that room. There'll be 3 or 4 people per room, and you'll take turns presenting, and then visitors who want to hear about different students' projects will just pop in and out of the rooms and listen to the presentations and possibly ask questions and so on. And that's all going to happen on Monday. And the whole SLP presentation runs from 10 to 12 basically, but our class is just in that second section. And Izad has 10 o'clock, 11 o'clock classes, so his students will be doing it in parallel with this, and so that's the basic setup. Solving problems recursively is it gets to be a challenge to not do things recursively eventually. It is a mindset, but after you've seen a few examples of recursive solutions and you've worked through some of it, your brain, most people's brains seem to latch onto that idea and start finding, lots of ways to do things recursively. And you can apply this in life, right? How do you do your homework? Well, first do the first problem, and then, call the homework function on the remaining set of questions. right? That's a 2-line algorithm for doing all of your physics homework, right? But the detail there is that, you have to do that first problem, and then you just pass it on to, someone to do the remaining problems. Well, that someone is you, right? But the algorithm is 2 steps basically. And the base case is when you get the homework with no questions on it, and then you just, return. There's nothing to do. I don't know if you do your homework or not. That's an open question. Oh, yeah, no base case. That's a bummer. Yeah, I guess it's possible to generate homework questions faster than they can be done. And that's an interesting question for recursion also. If you're using a recursive solution to a problem that's dynamic and is changing while you're recursively solving it, that can get into interesting questions. And we'll actually deal with some of that in 223 when we talk about multiprocessing and threading in Java, and this notion that you may have a process doing something on some set of variables, but there may be something else that's manipulating those variables, and can that be done safely, and can that get us into trouble? So why is it called dynamic programming? I don't know, and I really don't find a lot of comfort in that name. I don't know what the etymology of it is, but it doesn't sound very dynamic to me, and it doesn't sound like programming in particular. So I'm not sure about that term, but that's the way that I was taught it, and that's the way I've always seen it referred to, is just this notion of saving results. But it feels like it's probably a bigger term somehow. But we'll stick to its usage the way we have been. Let's see. Journey of 1,000 miles starts with a single step. Yeah, that's recursion, and that's an example I actually use in 215 to talk about induction, which is the same thing as recursion. All right. So the max val function we were doing yesterday. Hopefully no questions about that. Well, hopefully if you have questions about that, you'll ask them. Let me go back through the actual assignment, and let's make sure we've got all the details. So, inventory file, which you can find a sample of on the server, but you can also make your own, and I encourage you to make your own to develop your code and test it, and put in values that you can predict what the behavior of your program should be. So read the inventory file, echo its contents, right? So just show the item value and weight. I'm not being super picky on formatting in here. I'm going to leave it up to you to make good choices. And then use your max val function to calculate the maximum value and the count of each item that gives you that maximum value. Use dynamic programming, so cache your results, read them instead of iterating, and do output that looks something like this, right? Now it doesn't have to be exactly like this. If your name comes first, or you do value weight or something, I'm okay, right? But I'd like to be able to see the list of items in your item file, the capacity of the bag, the maximum value, and the count of items that get you that value. basic error handling would be if you don't have exactly 2 arguments on the command line, if the first argument is not an integer, or if there's a problem in the inventory file. So if it's not a string followed by 2 integers, then you can have your program throw up and exit. And again, simplifying assumptions, 128 items maximum in the item file, so you can make a static array of size 128. You can do parallel arrays, or you can make a structure for storing the name, weight, and value of each of your items. Maximum bag capacity is 1024, which means you only need 1025 entries in your cache to store all the possible capacities from 0 through 1024. You may not need the 0 depending on how you do it. And the first field in the item file, the name, is 32 characters max and does not contain any spaces, which means you can pick it up with a simple %s and you can save it in something with a fixed length of 32. You don't need to dynamically allocate that, right? Because we're bounded by 128 items. 128 times 32 is not a ridiculous amount of space. So no mallocs, no dynamic memory necessary at all. And then I don't know if I got through this yesterday or not, but let me just run through it again quickly. Pretty straightforward grading rubric. So this is now due on Tuesday. I have not changed this, but I changed it on Canvas. Okay. Yeah, I'll probably go ahead and change this. If the repo is not available Tuesday morning at 8, it's a 0. Okay. If you get it in 5 minutes late, if you've got everything working today, but you forgot to add me as a reporter, it's still a 0. Okay, I'm not going to be able to make multiple iterations of downloading and grading and so on. Still going with knappack as the repo name. And so this will work or it won't work, right? You have sample files, you can make sample files, there's a sample executable. You'll be able to tell if this is working or not. Usually, it's going to do one of the following things. It's not going to compile, right? That's 50 points off. It's going to seg fault. That's 50 points off. It's not going to generate a solution at all. It's going to run forever or not print out anything. Or it's going to come up with an answer, but it's not the optimal answer or an optimal answer, right? Or your dynamic programming doesn't work, and when I try to run this with 10 items, it takes, the lifespan of the universe to finish. So if it seems to be working for you on, more than the simplest possible test cases, and it's giving you the same solution as the sample code, you're probably good for, 100 points. And I'm not going to put in here deductions for, commenting or having your name in your code or things like that. But I really, really want to see those things. Okay, and if people stop doing those, then those will become, point value deductions in the future. So keep the good habits going. Okay. No more ODPs for this quarter. I may do some for 223, but we're done with them for now. That last batch of, I think, 3 ODPs, I still haven't uploaded those grades yet to Canvas, so those still look like zeros or missings, but I'll get those uploaded in the next few days. All right, so any questions on logistics for PA5? We've been mostly talking about, the knapsack problem itself, but is everybody clear on the programming assignment itself? Awesome. All right, so just a final note up there. It's due on Tuesday, not Monday. The rubric says Monday, but change that to Tuesday. All right, cool. We're good with that. Um, a recursive program that cannot be solved optimally without breaking down into subproblems or its recursion is a part of the larger solution. Yeah, I can hang with that. Um, and this knapsack problem and the problem we're about to talk about, the rod cutting problem, um, these lend themselves well to dynamic programming because they have the following properties, right? You can express the solution to one problem in terms of the solution of smaller problems, right? So you can break it down into this sub-problem structure. And by solving these smaller sub-problems, you can take those solutions, put them together to get a solution of the bigger problem. And generally, when that's the case, you've got probably a good candidate for doing some caching of your results, because it's typically going to be, a lot of deep recursion. So let's talk about a similar problem, which is rod cutting. And so the idea here is, imagine that you have a piece of material and it's got a certain length, and you have the ability to cut this into pieces. I think it was mental recursion that I mentioned was a cool band name, but deep recursion is also good. Or it could be like a fusion band between Deep Purple and mental recursion. It could be like the 60s spin-off. All right, so you have a bar of material, a rod of material, and you can cut this into lengths. Oh, nice. I like it. And the idea is that, this bar of material may be worth a certain amount as it is. You could simply sell it and get a certain amount of money for it. But it may be that if you also cut it into smaller pieces, you could end up getting more money for it. Because having, a 12-foot piece of metal is useful if the person buying it either needs a 12-foot piece of metal or has a way to cut it into smaller pieces. But if you could offer to cut it into small pieces for them, that's probably a value-added proposition, and they might be willing to pay more for those cut-up pieces. So we have a pricing table. Which looks something like this. There's a length, and there's a value. And these are going to be arrays. And, in a real-world situation, I could cut this rod into any length that I want. But it may be that, I'm not going to do that. It may be that I'm only going to offer, certain lengths. 1 inch, 3 inch, 4 inch, 6 inch, 12 inch. But, for simplicity, we'll just assume I can cut it into, any length that I want. And there's a value for these, right? So let's say this is a 12-inch piece of steel, and maybe to sell the whole 12-inch piece, maybe that's worth $10. And if I sell off a 6-inch piece, maybe that's worth $7. So yeah, somebody could buy a 12-inch piece and cut it themselves into 2 6-inches and save a few dollars, but maybe somebody doesn't have that equipment, and maybe what they really need are these 6-inch pieces, and so they're willing to pay $14 for 2 of those instead of $10 for a 12-inch. So we could have, different lengths like this, and maybe, nobody wants a 4-inch piece, so that's really inexpensive. And maybe 3-inch pieces are really valuable, and maybe 1-inch pieces are, pretty valuable too. So you have some kind of pricing table. So you can see where this is going, I think, right? The whole question is, what is the maximum value that we can get by cutting up and selling the pieces of a piece of material of some initial length. So max val 12 would say, you know, if this is our pricing table, how should I chop up my 12 inches of bar and sell it off to get the maximum value back? And you know, if I don't cut it at all, I get 10. If I cut it into 2 6s, I get 14. If I cut it into 3 4s, I'm going to get 6. That's not a really good proposition. If I cut it into 4 3s, I'm going to get 16. That's pretty good. If I cut it into 12 1s, I'm going to get $36, right? That may be our best bet. Yeah, so currently it looks like cut it into 1s. So we want an algorithm to be able to systematically figure out what this maximum value is. And it's exactly the same setup as our knapsack problem. We're going to make a first initial cut, and it could be, you know, in this case, anywhere from 1 to 12, or maybe 0 to 11, depending on how you look at it. So if we start off with a 1-inch piece that has a value of 3, and then since we've taken off 1 inch from our rod, we have this much material left that we could cut and get a maximum value of that. Another possibility is we could cut off a 2-inch piece, which is also worth $3, but we've taken 2 inches off of our length, and so we can get the maximum value from that. Or if we start by cutting a 3-inch piece, that's worth $4, and then it leaves us length minus 3 inches to chop up, and so on. So we want to find the maximum of value bracket I plus max val of length minus len I. Right? And this is exactly the same, you know, at the heart of the knapsack problem. So you iterate over those, you figure out what the maximum of those calculations is, and you return that as the value of max val. And it's got the same caveats as before, right? If our bar is only 3 inches in length, so a 4-inch piece would have a value of 2 plus that. If our material is only 3 inches in length to start, we can't use that as one of our possible values. Right? We can't cut a 4-inch piece out of a 3-inch piece of material. Right? I mean, my last calculation would say I can get $12, or I can get $10 plus, you know, the length I get out of my original length minus 12. If I only have 3 inches of steel, I can't cut off a 12-inch piece, so I can't get that $10. So we're not going to do these calculations if the length of our bar is less than the length we're trying to cut off. Right? So same as in the knapsack problem. If the item weighs more than the capacity of your bag, you don't take that into account in your calculations. But you do this and you get your max val, and it bounces back up through the recursion, and this will give you the maximum value that you can get from a rod. All right, let me make a quick comment about this business of finding the maximum value. And this trips people up sometimes, but I don't want it to trip you up. So our rod cutting example, So let's say we have a pricing table and it contains table length entries, right? Or this could be your inventory for your knapsack, and it would contain, you know, number of items in inventory. So I'm just going to consider a for loop, right? For I equals 0 to table length. So I'm going to say possible equals value bracket I plus max val length minus length of I. And so this is my max val function for finding the maximum value I can get from a rod of length ln. And so I'm going to loop over all the things in my pricing table, and for each one I'm going to consider its value added to the maximum value I get from the remaining rod after I chop off something with that length. And that's going to give me what might be a best solution. Now my goal is to iterate over all of these calculations and find the largest value of this. And so don't try to save them and find some maximum function that takes, you know, an array of values or something like that. Just do like a running sum. Do a running maximum. So I'm going to start off with some largest variable, which I'll initialize to 0. And then, if possible, is bigger than largest. Then I'm just going to save that possible value in my largest variable. And when I come out, largest will be my maximum value. It's kind of like a cache of 1. But it's also like, you know, doing a running sum. When you want to do a running sum of some calculation, you don't do your calculation and save all your results and then go through and add them up. You start off with, you know, a sum of 0 or a product of 1, and you keep adding to it as you go. Well, here I'm starting with, you know, a largest of 0, and each time I calculate a possible largest value, I just see if it's bigger than the largest I found so far. And if it is, then I save that as my current largest value that I've calculated. And when I'm done, this will be the largest calculation that I made. And remember, we need to make sure that this is physically possible. So I'm going to put around all of this. If length of I is less than or equal to the length of the rod that we have, and do all of that inside there. And this automatically takes care of your base cases, right? Because if I've got, you know, a rod of length 3 and there's nothing in my pricing table for a length smaller than 3, I can't cut my rod up, right? Well, none of these if statements are going to fire, and I'm not going to calculate any possible max values using this equation. When I come out of here, my largest is going to be 0. That's what I want to return. And this works for the knapsack also, right? If your capacity is 3 and every item in your inventory weighs more than 3, what's the max value you can get out of that bag? 0. Right? And this will dutifully return that, because, you know, we won't do any calculations to say, well, I could put this item in and, you know, add the value of that and find the max val of this capacity, right? So this will work nicely, you know, or something like this. But don't get bogged down looking for, you know, the right way to do this. A lot of times, when people are learning programming, there's a tendency to get brain locked on how to do something because nobody has told you how to do it, because you never learned a function for doing that, right? You can always write this stuff yourself, and in fact, more often than not, you should be writing it yourself. If you can think of how to break down the problem into a series of steps that do what you want to do, that's the way to do it, right? Yeah, there may be something out there that does this for you, but, you know, you're much better off just doing this. It's good practice, you're going to understand it better, and you can build on it down the road. So don't get curtailed by, well, I don't know how many numbers I have. How do I find the maximum of an unknown number of integers? Right? Just roll it by hand. Now the other thing for knapsack is, remember, we need to know not just what the largest value is, the maximum value we can get from a bag, but we need to know the inventory of items, right? We need this final inventory. So in here, when you're saving your largest value so far, you also need to be saving the corresponding inventory and then returning that somehow at the end. And that's just programming detail. All right, so that's the rod cutting problem. It's got the same structure of breaking this problem into recursive calls to smaller versions of the problem, so it works well with dynamic programming. And here, in the very beginning, I would check my cache. If I find the cached value, return that. Otherwise, do all of this, and before you return at the end, save your answer in the cache. All right, so any questions on that? So let's talk about tries. So one of your quiz 5, I think, talks about tries. And tries are a tree-like structure that we can use for storing and retrieving information really efficiently. And they're not binary trees, they're n-way trees. They tend to be very wide. And it's a clever structure. So let's think about just storing words, and our words are comprised of uppercase letters. So every character in the string that we're storing is one of 26 characters, uppercase A through uppercase Z. And so a single node in our trie looks like this. It's got 26 pointers. And we call these pointers A, B, C, D, E, F, up through Z. Okay, so really wide nodes, 26 pointers. Instead of just a left-right for a binary tree or just a next for a linked list, we have 26 pointers in each node. And we also have a flag over here, which we call EOW. That's just an integer field. It's a 1 or a 0. And we build a tree out of these nodes and use that tree to store information. So here's some sample nodes we can play with. And let's suppose we want to store the word cat. Okay, so any node that I'm not showing an arrow off of, we're going to assume that node is pointing to null. So we're just going to start off with one node here. In fact, let me do this the right way. All right, we're going to start off with one node. All of these things are pointing to null, and this EOS field is a 0. Okay, and we want to store the word cat into our trie. So here's what we do. We take the first letter of cat. We go to the pointer associated with C. It's not pointing to anything. It's null right now. So we create a new node, and we have C point to that. And now we go on to the second letter of our word. That's the letter A. And we look at the letter A. That's not pointing to anything. It's null. So we create a new node, and we have our letter A point to that next node. And now we take the third letter of our word T. We look at the T pointer in this current node, and that's null. So we create another node, and we have T point to that. It's always pointing to the beginning of the node. All right, T is the last letter in our word. So in the node that we just created and had T point to, we set this end of string field to a 1. All of these are zeros. Voila! We have a cat stored in a trie. Okay, this is a different kind of tree. If someone asks, is there a cat in this trie, what are we going to do? We're going to start with the letter C. We're going to say, well, maybe, because that points somewhere. We're going to come here. We're going to move to the second letter A, and we'll say, oh, A is pointing somewhere, so maybe there is a cat. We'll follow that to another node. We'll look at the third letter T. T is not null, so yeah, maybe there is a cat. That points somewhere. We've gone through the last letter of cat. This new node that we're in, we check the end of string flag. If that's a 1, yeah, there's a cat. It's not really a 2D array because we don't know. I mean, these nodes are always 26 across, but these are going to kind of bounce around a little bit. You might be able to implement this with an array, actually, now that I'm saying that out loud. But let's think about it with pointers, because I think it gives us more flexibility. So suppose we want to store the word cab. So we're going to start with a C. That's pointing to another node. So we'll come down here. We'll look at the A node. That's pointing to another node. We'll come down here. We'll look at the B node. That's pointing to nothing. So we need to have that point to a node. So we're going to have B point to, another node. And that's the end of our string. So we're going to set the end of string field in there. And we've stored the word cab. Alright, if we want to store, the word hi, we'll come over to our first node. So this is always the root. So we'll start at the root. We'll come over to the H node. H is not pointing to anything, so we'll have that point to a new node. And in that node, we'll look at the letter I, and that's null, so we'll have that point to a new node. And in this new node, we'll set the end of string to 1. That tells us we have the word hi. Alright, is there a car in our trie? We'll start from a C, follow that to another node. There's an A, follow that to another node. Check the R. R is null. Nope, there's no car. Alright, let's put California into our trie. So we start from the root, we look at the C, that's pointing to another node. We look in this node, there's the letter A, that's pointing to another node. We go into that node. This is a 0, which means there's no CA in our trie right now. We change that to a 1. We've just added this to our trie. So the advantage of this is it's really fast to do search. If I want to search for a word, I don't have to check multiple entries to see if this has the word, does this have the word, does this have the word, right? For each letter, I follow a pointer, and when I'm done, I check to see if I've hit something with my end of string flag set. If I haven't, or if somewhere along the way my pointer is null, I know my word's not contained in my trie. So what is this? This is basically order 1. It's really order the number of letters in your word, but if we use this for, say, the English dictionary, right, I don't think there's any English words with more than 40 letters in them. And so this is bounded by 40 operations, no matter how many words we store in here. Right? 215, how many 40-letter words are there? 26 to the 40th. But we can search that huge collection of data with 40 operations, and typically fewer. If most words have 8 letters or fewer, 8 operations, we can retrieve something from here. And, in addition to having this flag here, we could have some kind of payload that stores, the definition of a word or the pronunciation or, a cross-reference to other words or whatever we want. But it's basically a way to access information in this potentially huge collection with a minimal amount of effort. Yeah, you could use this on Scrabble, definitely. And traversing this is really fun. This is fun to code. I recommend it when you want to break. Coding up a try is fun because you get to make an array of pointers and you get to malloc them in a for loop and so on and so forth. And traversing this is really fun, right? What do? You start with the letter A, and if it's null, there's nothing that starts with an A. Go on to a B, that's null, there's nothing that starts with a B. Go to the C, well, there is something that starts with a C. So I can traverse from this point on down, right? Traverse the try starting with this root, and every word that I'm going to print out, just prefix it with a C. So I'll get my cab, and I'll get my cat, and I'll get my California. And so super iterative, super recursive, right? Or you could, do it iteratively with stack. But basically each one of these, you just follow it down, and then each thing in here is going to correspond to the second letter of a word in your try, and follow each of those, and wherever you follow it to, each node in there is a potential third letter of your word, and so on. So what's the downside of this? Why don't we use this for everything? I'll let you go after you tell me that. Takes up a ton of space. This is a classic space-time trade-off, right? Potentially, each branch of your try has 26 children, and each of those children have 26 children. So if this was a completely filled tree with a height of 10, you've got 26 to the 10th nodes inside this try, right? That's a lot of storage. But very, very efficient time-wise. And that's the classic trade-off we'll keep coming back to. So yeah, if you have limited possibilities, this is a really good option. Space-time trade-off, that's my mantra, actually. That's been, the past few decades of my life, is researching that. All right, cool. Have a good afternoon. I'll see you next time. Thank you.